So today's focus is interpreting probability in general, and then we're going to use simulation to model something that's actually happening in real life. So we're going to start out, of course, with an example. So if you could find this page, you're going to have to go through a few of the pages that have the multiple choice on them. As a special promotion for its 20-ounce bottles of soda, a soft drink company printed a message on the inside of each bottle cap. Some of the caps said, "Please try again," while others said, "You're a winner." The company advertised the promotion with the slogan, "1 in 6 wins a prize." The prize is a free 20-ounce bottle of soda. A stats class wonders if the company's claim holds true for the bottles at a nearby convenience store. To find out, all 30 students in the class go to the store, and each student buys one 20-ounce bottle of the soda. 3 of them get caps that say "You're a winner." Does this result give convincing evidence that the company's 1 in 6 claim is inaccurate? Design and conduct a simulation to estimate the probability of getting 3 or fewer winners if the company is telling the truth. Okay, so here's what we have going on. We expect out of the class that 1 in 6 would be a winner. What actually happened is that 3 out of the 30, or 1/10, were a winner. Now, based on that, our actual is less than what we expected to happen. Now, why is that? So there's 2 possible reasons, right? We expected 1/6 of our students to be winners, only 1/10 were. Why could that be? Well, the first one is, of course, the company is lying. Right? The company's lying. 1/6 are not winners. It's some number less than 1/6. Or we got this sample just by chance. Just by chance variability. So is it true, or is it possible, that in this store, 1/6 of the bottle caps were winners, and we just happened to choose a sample where less than that were winners? Is that possible? Okay, so the whole point of stats is figuring out which one of these is more likely. Is it more likely that just chance variability, we only got 3 winners, or is it more likely that the company is lying? Okay, so this is what we did in the last unit. You guys remember one of the last things you talked about was statistically significant, and you had those dot plots? That's what we're doing here. We're going to create the dot plot. So we're going to design a simulation and carry it out to figure out which one of these is more likely true. So here is the part that is really new, is the design. Okay, so we need to figure out, we're going to use a random number generator. We need to figure out how we're going to use that generator to simulate what is actually going on. So we are going to assume that this company's claim is true. We're going to assume that 1/6 are going to be winners. So what I'm going to do is I'm going to let the numbers 1 to 5 represent losing, and 6 is going to be a winner. So I'm only using 6 digits, bless you. One of them is a winner, the other 5 is losing. So this represents the claim by the company, which means we are going to ignore 0, and we're going to ignore, oh, we don't even need to say that. We don't even need to say that. Okay, we're going to use a random number generator. So we will use a random number generator with bounds 1 to 6. Okay, so now we need to go back to what's happening. What we are simulating is 30 students going into the store. So we need to simulate one class of 30 people buying a soda. So we are going to simulate 30 numbers. Okay, are we going to use replacement? So if I get the number 3, can I get the number 3 again? Yeah, it doesn't represent a specific person. These numbers in general just represent winning and losing. So we are going to simulate 30 numbers with replacement. Okay, so then we have to think about what are we looking at in these 30 numbers. So we're going to generate 30 numbers. What do we care about? So it says, conduct a simulation to estimate the probability of getting 3 or fewer winners. So all we care about in our trial is did we get 3 or fewer winners. So this is one trial. We are going to count the number of winners, which is the number of 6s. We're going to record, and we will repeat for a large number of trials. Large number of trials, if we were doing this on a computer, we would have a computer do probably 1,000 trials, 10,000 trials. We, of course, are not going to do that many. So we are going to do a small simulation in here, just all of us, and record on a dot plot. So in a minute, what you're going to do is I'm going to have you take out your calculator, and what we care about is the number of winners that you get. So what I need to know from you all is how many winners that you got. Did anybody in their sample have 0 winners at all? I'm just asking us to raise hands, and I'm going to put dots for each of you. Did anybody have only 1 winner? 2 winners? 3 winners? 4 winners? Okay. So 1 person with 4 winners. 5 winners? Okay, 3. 6, 3, 7. Okay. 8. Okay, so that's 5. 9. Did anybody get more than 9? No. Okay. Beautiful. So in our dot plot, every dot represents 1 sample of 30. So you all have seen this before from the last unit. So this 1 dot represents 1 sample of 30, where 4 people were winners out of the 30. Okay, so then what we're going to be looking at, where did our sample actually fall? So we really had 3 out of 30, which falls here. Based on our dot plot, is that a very common occurrence? No, that's pretty rare. So our sample is pretty rare. So now we're going to go back to which of the following do we think is more likely? Is it more likely that the company is lying to us, or is it more likely that we got our sample just by chance variability? Now, based on our dot plot, how likely is it that we would get 3 out of 30 just by chance? It's not very likely at all, right? So did we get this sample by chance? Probably not. We probably didn't. So we have evidence that maybe the company is telling the truth. Not telling the truth, rather. So we would say we have convincing evidence that the company is not telling the truth. Because we got the probability of 3 or fewer winners to be about 0. Now, does it mean that it's impossible to get 3 winners? No. It's just very unlikely. Okay, That's the idea. Most of what you're going to be doing in this section is just this part. For the most part, you're not actually going to be carrying it out, you're just going to be designing it. Questions for me before we go on and talk about a little more formal things? Okay, so that was the background. This relates to the law of large numbers. Do you think our dot plot would be accurate if I did only 5 samples? Probably not. 10 would be better, right? 100 would be even better. 1,000 would be even better. That's the law of large numbers. Law of large numbers says, as the number of trials increases, the proportion of some event, our event being the number of winners, gets closer to the true probability. So the probability of getting 3 or fewer winners is probably not 0. If we did this 1,000 times, we would probably get the true probability, or at least get very close. Simulation is often used when you don't know how to calculate a probability, which is our case right now. We haven't done any of the actual calculations. Okay, how do you interpret a probability? A probability is the percent or proportion of successes in the long run. By long run, we just mean large number of trials. So if you were to do this over and over and over and over again, we would get the true probability. Okay, some things for you to be aware of. First thing is when you're doing probabilities on your calculator, please be aware of scientific notation. The other thing that we need to know is that probability, I am super picky about this, but probability is always between 0 and 1. So it does not make sense to say the likelihood of rain today is 75%. That doesn't make sense. The probability of rain is 0.75, not 75%. That's why we need to be careful of scientific notation, because students will sometimes say the probability is 6. That doesn't make sense. Okay, let's talk about interpreting probability or seeing an example. The probability of getting a sum of 7 when rolling 2 dice is 1/6. We're going to interpret this value. A lot of times people will just rewrite that same sentence. The probability of rolling a sum is 1/6. Of rolling a sum of 7 is 1/6. That's not the case. It's a long run average. So if we were to do this many, many times. So in the long run, if we rolled 2 dice many times, we would get a sum of 7 about 1/6 of the time. When I'm grading questions like this, what I look for is in the long run and many times. So in the long run and many times. This is pretty much what we have to talk about today. So what we're going to be doing is just a few more examples and talking about some misconceptions. But this is pretty much the process for today. Any questions before we do a few more examples? Okay, so some things I want to talk about. Some myths about randomness. The biggest mistake, or the most common, is applying the law of large numbers to a small number of trials. So if I find a coin on the ground and I want to know if it's a fair coin, so is heads equally likely from tails? If I take that coin and I flip it 10 times and I get 3 heads, and I say, well, the coin's not fair then. That's not the case. Law of large numbers doesn't apply there. Flipping a coin 10 times is not enough. So of course your natural question is, well, how many is enough? There's no real number. Depends on the situation. The other one, and this is a really big one, even for people who know stats, is using the past to predict the future. Again, like if I were flipping a coin. If I flip a coin and I get 3 heads, and it's a fair coin, what's the probability on my next flip that I'm going to get a head? Still 50-50, right? It's a fair coin, unless I don't know that it's a fair coin, in which case that changes things. Just because you get 3 heads doesn't mean the next one's going to be a head. Okay, so purpose of a simulation, you guys have already seen this, is to estimate probabilities. That are difficult to calculate theoretically. So after today, you're going to learn some of the rules of how to calculate probabilities, but right now we don't know. And so if we don't know, we're going to use a simulation. And then sometimes there's situations where even theoretically, we don't know how to calculate them. So, for example, I think you guys know Mr. Plate has his master's degree in stats. That's kind of his area of expertise. When I was in grad school, I was interested in the likelihood that you have a baseball team that goes 100 years without winning a World Series, like the Cubs did. Well, to calculate that, that's pretty tough. I really don't know how to, and most people don't. So you design a simulation, right? And then you can change various aspects of your simulation. That's why we use this. So, okay, 4 steps. What do you need when we say describe a simulation? First thing that you are going to do is describe what the numbers represent. And then you're going to tell me, are you using replacement or not? Then you're going to describe how to carry out the process. And along with that, when are you stopping? So in the example we did, we stopped after 30 students. And last step is you need to say, what are you counting? Off to the side, I want us to write down what are the options, what are you able to use when you're doing a simulation? The first option, like we did, is a random number generator. You have to use that term. Do not say randint or RNG. You need to write out, use a random number generator. And then, just in general, other. And you're like, what does that mean? You could use dice. Maybe you could use a coin, although I wouldn't suggest it. You could use the hat method, or you could use a table of random numbers. I would suggest you just do random number generator and table. On the AP test, College Board cannot check you using a random number generator, right? College Board can't see what's on your calculator. So if you ever had to do this on the AP test, you would be forced to use this table. And we'll talk about doing that. Okay, at this point, we have 2 or 3 examples to do. Questions for me before you guys do some examples? Okay. So, did you guys, the very beginning of this class, like the first or second day in class, did you see the video with Joy and the Parkinson's disease? You guys didn't see this video? Okay, cool. Well, this is new to you. So there's this woman, Joy Milne, who's in the UK, and she smelled some type of funky odor on her husband that she had never smelled before. He was then diagnosed with Parkinson's disease 6 years later. And so what she started to do is she started to go to these support groups with her husband. Support groups that had other people in them that had Parkinson's disease. And when she went into these support groups, she had this overwhelming sense of that smell. And so she started to suspect that maybe Parkinson's disease had a smell. She had only smelled it on her husband and then in this room with this support group with other people that had Parkinson's. And so an experiment was done. And she was given 12 different shirts, just randomly. She was given these 12 shirts, she smelled them, and the question was, does that person have Parkinson's disease or not? And so out of those 12, she identified a certain number correctly. Before I tell you how many, if she's guessing at random, what is the likelihood that she would guess correctly if the person has Parkinson's or not? Should be 50-50, right? So assuming that she's guessing at random, what is the likelihood that she will guess correctly? Should be just 1/2. Which means she should identify, or we would expect her to identify, about 6. Ooh. Okay, about, 6 correctly. Now, that being said, she actually identified 11 correctly. That's pretty crazy, right? And then, fun fact, you want to know this? So she identified 11 correctly. The one mistake she made is there was one person that she smelled the shirt and she said this person has Parkinson's disease, and they didn't. They developed Parkinson's disease 6 months later. So it turns out she really could smell this. Now, what we're going to do is, knowing that she guessed 11 correctly out of the 12, we're going to design a simulation to estimate that probability. So what is the likelihood that she would identify 11 or 12 of the shirts correctly? This one we're going to do together, and then you all will do an example, and that'll be it for our notes. Okay. We are going to use instead a random number table. Have you all seen a random number table before? Has Mr. Plate shown you that? Probably not. Okay, so first thing that we're going to have to do is we're going to have to define our digits. In this case, what we care about is with each shirt, she either identifies correctly or she doesn't. We have 2 different options then. We could just use numbers 1 and 2. 1 is correct, 2 is incorrect. What is going to make that a little difficult with our table?
So the numbers besides 1 and 2.
Yeah, other numbers besides 1 and 2. So we can do that, but do you recognize we would have to skip a whole lot of numbers? So probably not the best option. So what I'm going to do instead is I'm going to say let numbers 0 to 5, nope, not 5, 0 to 4, right, because that's half the digits. So 0 to 4 represent identifying correctly. So then 5 to 9 are incorrect. Again, 1 and 2, totally fine. You also could use 2 digits. So then I'm going to look at the table. And I'm going to consider one digit at a time. Bless you. Am I using replacement? Yes, these numbers don't represent specific items. It just represents in general correct or not. So we are going to use replacement. In real life, we're having Joy look at 12 shirts. So we are going to stop after 12 digits. And we are going to count the number of correct identifications. Correct, again, just being the numbers 0 to 4. And what we have to make sure we say is that this is one trial. Repeat many times. Okay, that is it. That's describing the simulation. Like I said, most times you're not actually going to be carrying it out. You're just going to be describing it. Okay, so things. If you go to the next page, common errors when using a random table of digits. There's two common ones. The first one is not using the same number of digits. So for example, people might say 0 to 7 is win, but then 8 to 12 is lose. That doesn't work. This has one digit, this has one digit to two digits. Everything either has to have one or everything has to have two. Those are the only two options. So in the case here where we're getting up to two digits, to 1, 2, everything would have to have two digits then. So I would say, okay, 0, 0 to 0, 7 is a win, and then 0, 8 to 1, 2 is a lose. Everything has two digits then. The other common issue is what do we do with numbers that are not used? So if we were only doing 0, 0 to 12, we would need to specifically say in our design that 13 to 99 we would ignore. So we're going to ignore any numbers that don't have a definition. Those are the two most common issues. Okay, questions for me before you all try one on your own. Okay, so we're going to read this one together to make sure we're all on the same page in terms of what's happening, and then I will tell you what I expect. So suppose I want to choose a simple random sample of size 6 from a group of 60 seniors and 30 juniors. To do this, I write each person's name on equally sized pieces of paper and mix them up in a large bag. Just as I am about to select the first name, a thoughtful student suggests that I should stratify by class. I agree, and we decide it would be appropriate to select 4 seniors and 2 juniors. However, because I already mixed up the names, I don't want to have to separate them again. Instead, I'm going to select names one at a time from the bag until I get 4 seniors and 2 juniors. This means that I may need to select more than 6 names, right? So if I get 2 juniors before I get the 4 seniors. Design and carry out a simulation using a table or a random number generator to estimate the probability that you must draw 8 or more names to get at least 4 seniors and 2 juniors. Okay, so this one's significantly more complicated than the ones that we've done. In a minute, I'm going to have you just chat with the person next to you and write down how are you going to define your digits and then try to design your simulation. Let's just use a random number generator. That I think is easier. And you're going to carry out 3 trials. Here is what I said. I'm going to use a random number generator that has bounds 1 to 90. I'm going to continue to generate numbers until I have 2 numbers 1 to 30, so 2 juniors, and 4 numbers 31 to 90, which is the 4 seniors. And then I'm going to count how many numbers I've generated. That's 1 trial, and I'm going to repeat many times. This most accurately represents what is happening in the real life situation. That being said, all we care about is, did it take us 8 or more names? All we care about is, did it take us 8 or more names? So what the group over here brought up is, could we just generate 7 numbers and be done? That's another way to do it. You generate your 7 numbers and say, did I get yes or no what I was looking for? And then I asked you to carry out 3 trials. So if I was doing this and I was recording, I would say trial 1 took me 7 names, trial 2 took me 6, trial 3, which I didn't do. Can somebody tell me one of their trials? How many did it take? 6. Okay, this one said, carry out your simulation and estimate. I told us in the last one we weren't going to estimate. We are going to estimate on this one. So last thing we would do is we would write a sentence and say, I estimate the probability that I must draw 8 or more names to be. So in this case, it never took me 8 or more names. So that happened 0 times out of my 3 trials. Which is 0. Now, what do you think a probability of 0 means? Never happens. Okay, do we think this is actually never going to happen, like in the long run? No. So what I often say is or very little. Because it's not impossible. It's just not going to happen very often. One thing for you all to recognize, this is just an estimate. This is not the probability. This is just an estimate based on our very small simulation. If we wanted this to be more accurate, we would have to carry it out a bunch more times.